All right, we're going to move on to chapter 14 now. Just like with the previous chapters, I'm going to ask you to do some of the legwork on your own as far as nomenclature goes. So with the ether chapter, you should review the section on nomenclature either in your book or watch the video online that I will post. I believe the section is 14.2. Otherwise, you can watch the Khan Academy video that I'll post online. It'll be nice and short, so it won't take much time. But we've already seen ethers quite a bit. If we think about ethers as a functional group, how do we normally represent them? ROR typically, right? So it's some sort of alkyl group on one side of an oxygen and another alkyl group coming off the other side. Oftentimes they're the exact same alkyl groups. A common solvent that we use in lab is diethyl ether, so each of those R groups would be an ethyl group. They're very commonly used as solvents. But they're very common functional groups in organic chemistry. They have a few unique properties about them. If we look at that oxygen, it's got two lone pairs on there, which means it can be H bond acceptor or hydrogen bond acceptor. In this case, can it be a H bond donor? No, we don't have any hydrogens that are attached to an electronegative atom. We only have alkyl groups. So in this case, it can only be a H bond acceptor. Along these same lines, it can be a weak Lewis base. So if we think all the way back to our acids and bases section, a Lewis base is something that donates electrons. In this case, the lone pairs can be weak electron donors. And in this case, it's particularly important because it can stabilize Lewis acids. So if we think back to our section where we were talking about hydroboration oxidation, we said that we had borane, which is trigonal planar. And the unique thing with borane is it's got this empty p orbital, right? Which means that this is a Lewis acid. It really wants electrons. So what do we normally have besides BH3 when we're doing hydroboration oxidation? THF, right? And so if we think about THF, THF is actually an ether. And in this case, it's a 5-membered ring that's an ether. And these electrons on the THF will stabilize the borane by donating electrons into that p orbital. So it's very common to see ethers being used anytime you're working with metals or Lewis acids. So for example, with Grignard reactions, we oftentimes use ethers because they'll help stabilize magnesium in the reaction mechanism. Another thing to point out about ethers is that they're fairly inert. They do react. We mentioned briefly that ethers degrade slowly in the presence of air through autooxidation. They're also reactive with really, really strong acids, and we'll cover that mechanism. But in the grand scheme of functional groups, they don't do a whole heck of a lot. They just kind of hang out. They're very common functional groups in drugs and solvents. In drugs and solvents. And I'm going to put down a few common solvents that are used very regularly in organic chemistry. I already mentioned a couple of them. The first one is diethyl ether. So it's got two ethyl groups on it. The other one that we already saw was THF, or tetrahydrofuran. And the last one that's common because it's a higher boiling point ether has two ether groups in it, and this is called 1,4-dioxane. So we can pick our ether. The nice thing about diethyl ether is it evaporates really, really quickly. We saw that in lab when we did the extractions. You can leave it out for a matter of minutes and it will evaporate very quickly. The problem with diethyl ether is it's not that polar, right? If we look at the net dipole for diethyl ether, those alkyl groups can spin around freely in space, which means that those vectors aren't all adding up and pointing in one direction. If we look at THF, I was always told that you can think of it like a dog with its ears tied back. It's diethyl ether, but we pulled both ethyl groups back, and now we've got a really nice, strong net dipole going in one direction. So THF is a very common polar ether compound if you need to pick a polar solvent that's inert. So same with 1,4-dioxane, it just has a much higher boiling point than THF. So those are the most common solvents. The other ethers that we've already been exposed to are epoxides. And I saw this online and I thought it was a really good explanation of epoxides. Let me move this up. All right. It's a family portrait of the ether family. I said that ethers are fairly inert, kind of bland. Molecules don't do a whole lot. But you notice the kid on the right? He's the epoxide of the family. He's a little bit more reactive, a little out there, doesn't behave like normal ethers. So epoxides are called the black sheep, or at least I call them the black sheep of the ether family.
That kid's actually on 20.
And we've already seen epoxides when we covered our alkene chapter. And epoxides go by a few different names, but we saw that we can make them by reacting a normal alkene with MCPBA, and we can get to this guy, which is just called an epoxide. It used to confuse me because occasionally people will call it by a different name. Usually older chemists call it by oxiranes. So you may see either of these nomenclature methodologies used when talking about epoxides. They'll either call them an epoxide or an oxirane. They're completely synonymous. There's also a few other ethers that I wanted to talk about. They're not common, but they're important to bring up. Want me to leave that up? It's OXIRANE. Well, this is why I'm not an English teacher. There's some other cyclic ethers as well. And you may occasionally find these in pharmaceutical drugs, but we're not going to spend a lot of time on them. I just wanted to show them to you. We've got the four-membered version of an oxirane or an epoxide, and this is called oxetane. You can have the five-membered ring version, which looks a lot like THF, actually, which is an oxolane. So one's a four-membered ring, one's a five-membered ring. It's just the size of the ring. And these keep on going on to different size rings. Really, the most important cyclic ether is going to be our epoxides, though. Yep.
Literally the exact same.
It's the same thing as THF, and oxolane is just the parent family, so we could have a functionalized oxolane. Yeah, same thing like we say benzene, but we know we can have functionalized benzene, right? So we can have functionalized oxalanes. Usually people will just call it by the IUPAC names, but you may occasionally run into these names. So we're going to study epoxides quite a bit in the sections that we'll cover next week. But I just wanted to introduce all of the classes of ethers that we'll be running into this quarter. We'll be running into normal straight chained ethers. We'll be running into cyclic ones. And we may even run into some unique ethers. I actually wanted to spend the last 5 minutes of class talking about my favorite type of chemistry. I've got a lot of favorite types of chemistry. But this is a special topic. I'm going to spend a little bit of time on this just because it's near and dear to my heart. These are called crown ethers. So we've got 4 oxygens, and they're each bridged with ethylenes. And so you can imagine these kind of look like a crown, right? So what this is called is 12 crown 4, because we've got 4 oxygens in it, but it's a 12-membered ring. It also has a similar one where there's 5 oxygens. Again, I've got double. No, I've got one more oxygen. 15 crown 5. And the last one I want to show is one with 6 oxygens. Does anybody know what the name for this one would be?
18 crown 6.
Yep, 18 crown 6. And the reason I wanted to introduce these is because they're very hot in chemistry right now. They're being studied quite a bit. Not these ethers in general, but the overall topic of host-guest chemistry. And what this means is that these ethers all have lone pairs, right? We've got lone pairs there. They all want to donate their electrons towards something partial positive, right? They're good electron donors. So in this case, what happens is a lithium ion can hang out on the inside of this, and those lone pairs will stabilize that cation. Conversely, if we go to 15 crown 5, lithium's a little small, but sodium's just right. If we go to 18 crown 6, which cation do you think fits in there? Potassium. So what this is called is host-guest chemistry, and this is actually what I got my PhD on at UO. And this is a big deal for a variety of reasons. The Nobel Prize was awarded in 1987 for host-guest chemistry. And what they were essentially doing was trying to mimic some of the things that are observed in nature. In particular, let's see if I can move this all the way up. Yeah, we'll move it up. This is vanillomycin. This is a common antibiotic. Or I wouldn't say common. It is an antibiotic. But if you look at it, it looks pretty similar to a crown ether, right? Crown ethers have all those lone pairs pointing into the center of a cavity. All of these lone pairs are pointing into the center of a cavity. And if we think about this, the potassium ion fits super, super snugly in there. So if we look at vanillomycin, which is antibiotic, it binds potassium 1 million times more strongly than sodium. So we're studying a lot of these host-guest systems because this is how our body works, right? Our body needs to recognize not only other neutral molecules, but oftentimes charged molecules or ions. So in this case, vanillomycin will actually wrap around potassium and be a potassium transport agent. And because of this, it makes a super potent antibiotic. And so it's one of the only antibiotics used for some of the exotic respiratory syndromes that you've heard about on the news. So like Middle East respiratory syndrome and things like that. They save these as last resort drugs because they have a very novel mechanism of action where they disrupt the ion balance across cell membranes. And you can tell that this is actually a peptide, right? So we'll cover peptides at the end of the term, but all of the bonds here are amides, right? So this is actually a naturally made cyclic peptide that's produced in a variety of bacteria. I really like host guest chemistry, and one reason that I think it's kind of cool and relevant is if we think about this reaction where we try to displace a bromine, and we run this reaction in benzene, we actually get no reaction. Right? Potassium fluoride is just simply not soluble in benzene. Fluoride's a terrible nucleophile. It's not going to happen. We can't displace off that benzene. But what might we be able to add to this reaction in order to make that fluorine or fluoride a better nucleophile? Not vanillamycin. Let's use something cheap that might not kill us if we add too much of it to our gloves or hands. In this case, I said potassium fluoride. So we need something to wrap up that potassium. Yeah, 18 crown 6. So if we run this reaction with bromine and potassium fluoride in 18 crown 6 in benzene, we can actually substitute off a bromine and get fluorine to act as a nucleophile, because now this fluorine is not bound tightly with an ion pair. The potassium is actually wrapped up in the crown ether, and the fluoride becomes a much, much better nucleophile. So in this case, the 18 crown 6 makes fluoride a better nucleophile. I think that's where we're going to stop today. We'll talk a little bit more about ethers next week and the reaction and preparations of them. Like I said before, make sure that you use this weekend to study and catch up, particularly if you feel like you're starting to fall behind a little bit. Use this day off to your advantage.